second last lecture of Engineering 5, and we're still talking double integration, and we're going to be looking at changing the order of integration. Now we did that, we looked at this in the last lecture, and I said sometimes it's easier to flip the order of integration because it avoids you having to use integration by parts. Sometimes it avoids you having to do integration by substitution, which are a wee bit more difficult. But sometimes integrals are actually, double integrals are impossible if you do it dx dy instead of dy dx, or vice versa. So let's have a look. So what we're going to be doing today is we're going to be our double integral and we are going to change that to or vice versa. So we're either going to start with dx dy and go to dy dx, or start with dy dx and go to dx dy. That's what changing the order of integration means, because we always do the middle integral first and the outer integral second. So internal integral and then outer integral. Now, what's important are the limits. Now, I've just said it's called the region R at the minute. Now, the internal limits okay, so for our internal integral, an internal limits describe the curves, right? So this is the curve or the line at the start right, and the top one is the curve or the line at the end of the region. Right? So these two are our two bounding curves. So it can be a line, it can just be a number, or it can be a function or a curve, right? So, i.e., we can have something like between 2 and x squared, right? That's the line y at x equals 2, and that would be the line x squared, y equals x squared. Okay? Now, the external limits. Okay, so this one here can only be numeric bounds, right? That's just numbers. I.e. between 0 and 1. Right. So how do we go about getting these? And remember, these are the bounds. So these are numbers that bound our region, and these are curves that bound our region, but they're all still lines in their own way. Right. Now, if we're looking at a region, right, so if we have the integral, the double integral, this pen's not working that well today. So if we have the double integral of the region R of dx dy, that means our curves are along the horizontal. So these are our curves or lines. And up and down the way, our y coordinates are external ones. can only be numbers. So these are numerical bounds. Okay? If we have over a region, but this time we're doing dy dx, that means that our curves are measured up and down the way. So the lower curve would go in here, the upper curve would go in here, and our numerical bounds go along the way. Right now, what I'm just trying to do is explain how it works. So it's going to be a little bit more easy to quantify later on. That's probably the worst horizontal straight line I've ever drawn. Let me steal the computer one. So the numerical bounds go along the way, and the curves go along the way. So if we get dx dy, the curves we measure by putting a pen along horizontally. Our numerical bounds we get by moving our pen up and down the way. If we've got dy dx, our curves go up and down the way, and our numerical bounds go along the way. Sounds like nonsense? Let's find out. Example 1. Okay, now this is one of the questions in a revision booklet I'm going to give you. It's example 1. Reverse the order of integration the following functions. It's 2x, y, and it's dx, dy. Now the crucial thing are what are our limits. So our limits here is y over 2 and 1 are our internal limits, and the function will tell you their external limits are 0 and 2. Right. So that's what the question would say. Now, in an exam or something that would be done on paper, without a computer or a graphing calculator or something, they'd need to give you the region of integration, right? So first thing I'm going to do when I take this question is, so remember we name our limits. So this is our internal integral. So that means that means we've got here x equals 1 and x equals y over 2. That's what those two limits mean. Y is an dy is an external integral, so that means we've got y equals 2 and y equals 0. Now that's the important thing that we need to do first. Right now, as I said, you'd then be given a diagram of this region. Right, but instead of doing that, I'm going to put these limits and draw it using that graphing software. So let's have a wee look. So we've got y equals 0 and y equals 2. So y equals 0. Okay. Y equals 2. And then it was x equals 0, I think it was. No, x equals y over 2. And x equals 1. Right. So let's have a zoom in. This is my region here. So I'm going to copy and paste this over onto my sheet. So as I said, you'd be given this in your exam. Right. Okay, so first thing, this is our region here. Right, now let's just label our region. So this here is x equals 1. This is y equals 2. This is y equals 0. And then our line, our blue line here, was x equals y over 2. Right. And remember, I'm doing dx by dy. So dx by dy means we're coming along the way. So our first line that bounds our region is our blue line, and our second line is our green line. Going up the way, our first line is this 0 line, and our top line is that line. So that means that this is our region of integration in here, right? Because it's the bit that's bound by all of those lines. So it needs to be inside the red line, the green line, the blue line, and the black line. So it needs to be inside all of those lines. And that's the region that's inside all of those lines. This bit here isn't. That's not inside the blue line. Right. So that's the way it looks just now. Right. So with that integration, that's the way it looks. So as I said, you go along the way, because it's dx first, you go along the way. The first line you hit is y over 2, which is our bottom line. The second line we hit is x equals 1, which is our top line. So that's us finished going along the way. And then if we went up the way, the first line we hit is y equals 0, so that's why it's our bottom limit. And the top line we hit is y equals 2. So that's why we've got this region here. Right, now, I want to change the order of that integration. Right, so what I want my answer to look like, or my question to look like, is I want it to look like dy dx. So, still got my region of integration, right? But my curve, or my straight line, which has got an algebra term in it, must be written as y equals, because it's dy that we're doing first. So if we're moving this line about, we could rewrite this line as, if we move that 2 across, it would be y equals 2x. Right. Okay, so we're looking from going up and down the way first. So we draw a line with our pen. Right. So if we draw a line with our pen, the first line we hit up and down the way is y equals 0. So that is our lower limit. Okay. Right. If we keep going, the straight line we hit in the up and down direction, which bounds this curve, is y equals 2x. So that's 2x. I'll just, I'll put in the y's and I'll put in the. So the first line we hit was y equals 0. And the curve that we hit, or the straight line that affects it massively, is this y equals 2x. Right? Then, going along the way. Now, going along the way is not, this curve can't have anything, or this straight line can't have anything to do with it, because it's got algebra in it. When I'm doing my external integral, it can only contain numbers. So if I go along the way, what's the number at which my region starts? Well, my region starts at 0, right? Okay, and it finishes at 1. And then the internal, the actual thing I'm integrating, doesn't change. And that is me change the order of integration. So whatever curve or line contains algebra, you change it round. So it was x equals y over 2. So y is the same as 2x. You then go up the way. What's the first line or curve you hit in the y-axis? Well, that's y equals 0. What's the second line or curve you hit? It's y equals 2x. Then going along the way, you're just bounded by the numbers. Where does the region of my integration start? Well, it starts at 0 and it finishes at 1. Right, So now we've just got to integrate. So do the internal integral first. X equals 1, x equals 0. Right, so I'm integrating this with respect to y. So that's going to become 2x y squared over 2. Because remember, we treat the x as if it's a constant, and if you integrate y, you get y squared over 2. And let's put in our limits. So that's between 2x and 0. I'll put in y there. Y equals 2x. And y equals 0 dx. I've got an awful habit of forgetting to put the y and x equals next to the limits. Please do it, it makes it easier. Right, let's simplify that because I can. So that's going to give me xy squared between y equals 0 and y equals 2x dx. Right, so we're going to substitute in our values in place of y. Right. Oh, so there's a 0. I suppose I should have equal signs going all the way down, but I'm using a new software today, so that's maybe why. Maybe it looks a wee bit clearer, and two, the little lines aren't disappearing all the time like they were when I was using that other software. So you substitute in the top limit, you substitute in the lower limit, and there we go. That's a squared, by the way. Right. So right, so if I square 2x, it gives me 4x squared. Multiply by x gives me 4x cubed. Anything times 0 is 0. So that's me done. So that's my internal integral sorted out. So let's integrate this again. So that's going to give me, so again, we go to square brackets because we're evaluating an integral. 4x cubed becomes 4x to the power of 4 over 4. You could have taken that 4 out if you'd really wanted, but I don't think it really makes it any easier. Remember, there's no plus c because it's an integral where you've got limits. So that gives me just x to the power of 4 between 1 and 0. So that's just 1 to the power of 4 take away 0 to the power of 4, which is just 1 unit cubed. Okay, so that's my double integration done. I've changed the order of integration by using my wee diagram, and I've got my final answer as 1 unit cubed. Right. So as I've said, as we go along, please make sure you keep writing x equals and y equals on your limits because it means you remember to substitute in the right one. Right, example number 2. I'm going to do quite a lot of examples on this, as I've said. Right, change order of integration, and we're going for this example here. So we're going for between 0 and pi by 2 of x and pi by 2 sine y over y dy dx. Okay, so what it's asking us to do is change the order of integration. So the first thing I'm going to do is, this time y is my external integral. So that means I write y equals here, and y equals here. And then here I'm going to write x equals, because it's my external integral, and x equals. Right. So that's where you'd be given the question. First thing, you put your y's on your limits and your x's on your limits. And then what we do is we get our graphing software up, or you'll be given a diagram of the region. So let's have a look. So so y is from x to pi by 2. You type in pi in these software, it gives you pi. Right, then I'm going from 0 and my x's to, again, pi by 2. Okay, so let's notice where our lines are. So we've got blue line, red line, green line, black line. Okay, so let's again copy and paste this over. In fact, maybe don't like how big a picture I've taken in that, maybe take a wee bit smaller. Right. So that's my diagram as I have it. Right, so let's label what we've got. So this black line here is y equals x. Right, this red line is y equals pi equals pi by 2. Right, that blue line there is x equals 0. And that green line there is x equals pi by 2. Right, so let's look at the region that they're saying. Right, so the region that they're interested in, because we're going up the y coordinates first, is the one that starts at y equals x. It starts at this line here and goes up to this line here. So this is my region here I'm interested in, because my limits tell me that it starts at y equals x and goes up to y equals pi by 2, and along the way it starts at 0, which is fine, and goes along to pi by 2 in that bit. So don't get it confused with that bit there. If that bit there would be the wrong region, because x hasn't happened yet vertically. Okay, so that's my region as described using my limits. So what I'm wanting to do is write this as the double integral, but dx dy. Right, so first thing I need to do is rewrite the line in terms of x. Right, so it's y equals x, so instead of writing y equals x, I need to rewrite that so it's in terms of x. So that's just going to be x equals y. Right, straightforward. Right, so but I'm now doing it horizontally, right? So because it's dx first. So what bound does it hit first? It hits first in my region x equals 0. And then the line that stops it going any further horizontally, because remember, the internal integral must contain the line or the curve or the something that's a wee bit interesting. So that's x equals y. Okay, and then here, if we look at vertically, well, vertically, my region starts, the first number it starts doing something at is 0, and it goes all the way up to pi by 2. So y equals 0, y equals pi by 2. So that's me change the order of integration. And my sine y over y stays exactly as it is. So let's integrate this then. Because that function before is something I couldn't integrate. It's horrible. Right, so that's just all a constant because it's in y, so I'm integrating with respect to x. That's x multiplied by sine y over y. And my limits are y, x equals y. Just write that a wee bit clearer. X equals y and x equals 0 dy. Okay, so let's substitute in our two limits. See, told you, keep forgetting to do that. You please remember to do it yourself. So that's y equals pi by 2, y equals 0. So I'm going to get y sine y over y. Take away the lower one, substitute in, so that's going to be 0 times sine y over y dy. Substitute the top limit, so in place of x, substitute the bottom limit in place of x. So that first bit and y equals 0. Those two y's cancel, so I'm just left with sine y. This bit here just gives me 0. So I'm just left with sine y dy. Right. So let's integrate that. So sine y, if you integrate sine, you get negative cos let's substitute that in. So that's negative cos pi by 2 take away negative cos 0. So that's 0 take away negative 1, which is again 1 unit cubed. The answer to these questions isn't all 1 unit cubed, it's just that those first two examples that I quite like, the answer is 1 unit cubed. Right, let's have a little look at another one then. Change the order of integration. I suppose you should put change the order of integration and evaluate for all these questions, because I do want to know what the answer is. Right, so the integral between 0 and 1 the integral between inverse cos y and pi by 2 of cos x dx dy. So that's the integral that I'm given. So step one, let's put in our limits, right? So our limits, we put, remember, x equals, because it's an x equals, because that's the internal integral, and then y equals, and y equals. And just add it into your question like that as you're doing it. Right, so now we've got these lines that I need to draw. So I need to go in my graphing software and draw x equals pi by 2, x equals inverse cos y equals 0, and y equals 1. Y equals 0, y equals 1, x equals pi by 2, which I've already got, and x equals inverse cos y, like that. Okay, so let's have a little look at my region this time. So y equals 0 is this line here, y equals 1 is this line here, x equals pi by 2 is this line here, and x equals inverse cos y is this line here. Right, so we were looking at it originally from the x perspective, right? So that tells us what our region is going to be, right? So in x perspective, the first line we get to is this line here, which is inverse cos y. The second line we get to in our region is pi by 2, and that's bound between 0 and 1. So that means this bit here is our region. So let me copy and paste that over. Oops. Right, so as I've said, it's dx what we're doing first. So the first line we hit in the dx, because remember we've got red line, black line, blue line, green line. They're all our lines that are bounding our region, right? This is an axis here. So if we go along, the first line we hit is this one here, in the x direction. That's that's the end of our region there. That's the first numerical bounding region, and that's the second numerical bounding region. So that means that this bit here is our region, right? This bit here. Okay, so let's label. So that blue line, which is an important one, is x equals inverse cos of y, right? That one is y equals 1. This one here was y equals 0, right? And our green line is x equals pi by 2, right? I don't really like the way I've done that. I'll write x equals pi by 2 further up. So I'll do it up here, x equals pi by 2. There's my green line. Right, so, but remember the curve that's got letters in it, when I change the order of integration, that needs to be changed around. So that needs to be made y equals something, because that's going to be my internal limit, right? So if I change the subject to that and make it y equals, that cos moves over to the other side and it changes from inverse cos to normal cos. So this means I get y equals cos x, right? So that line, that blue line, can now be called y equals cos x. Right, so I'm wanting to go to the integral, and I'm wanting to go from dy dx. So that means that I'm interested in what happens up and down the way first, and then along the way, right? So up and down the way, our first curve I hit is cos x. So that's my bottom curve, y equals cos x. And then that's bound by this line, y equals 1. Okay, let's look along the way then, right? So along the way, my region starts at x equals 0 and it finishes at x equals pi by 2. There we go. So there I have swapped or changed the order of integration, and remember the middle function cos x stays the same. Right, so let's integrate. So if I integrate this, cos x is a constant, so that just becomes y cos x, where y is equal to 1, y is equal to cos x dx. Right, so let's substitute in our limits. So that's going to be 1 cos x take away cos x cos x times cos x dx. I suppose you could put that in a whole bracket if you wanted, but hey, let's see how it goes. So I've simplified that down. So x equals pi by 2, x equals 0, so I've got cos x take away cos squared x dx. And notice I've only got x's now, I don't have any y's or anything, so I know that my change in order of integrations actually helped me. Now, this is the thing you've got to watch, and this is what happens in these types of questions. There's normally a bit of trig identity work involved, or sometimes there's integration by parts or integration by substitution involved. So this is going to be one with a trig identity involved. So this here, I can't integrate at the moment. But cos squared x has an identity which is a half plus a half cos 2x. And cos 2x is something I know how to integrate. Cos squared and sine squared I can't integrate. Cos 2x, sine 2x, sine 4x, whatever, is something I can integrate. Right, so I'm using this trig identity. Right, and the identities are on the formula sheet. They might look slightly different, but you should get there. So that means I've got the integral between x equals 0, x equals pi by 2 of cos x take away a half plus a half cos 2x dx. Okay, because I've just substituted this in place of my cos 2x. And remember, put it in brackets because there's two parts to your function that you're substituting in, and otherwise you're going to end up getting this sign wrong. Right, so that's going to equal cos x take away a half, take away a half cos 2x dx. And that's actually a lot easier to integrate, right? So let's do it. Right, so cos x becomes sin x. A half becomes a half x, or x over 2. This here, right, cos 2x, so that's a half multiplied by, and cos 2x becomes sine 2x over 2. And we're doing that between pi by 2, x equals pi by 2, and x equals 0. Now, in all aspects of maths, in engineering 3 through to 5, wherever you see a sin or a cos, your calculator must be in radians. Right? Radians is the standard measure we use. If you do this in degrees, you'll lose marks. So that gives me sine pi by 2, take away a half, times pi by 2, take away a half, sine pi by 2 over 2. I could have simplified that down, right? Take away sine 0, take away a half, times 0, take away a half, sine 0 over 2, right? So calculate it. Oh, that should be sine 2 pi by 2. So that's sine pi over, right, so we'll just watch that. There's a wee 2 in there that I've missed out, right? So if I work that out, that tells me that this bit is 0.2146 and a whole lot of other stuff. This bit here is just 0, so I've got 0.21 units cubed. So we have, in this example, got the computer to sketch the graph for us, worked out where our region is, changed the limits, so changed the region of integration, and just completed the integration all the way through. Now, you may have sine squared x, you may have tan or something like that, so whatever you get, make sure you remember to use the trig identity to make it easier to integrate. Right, now let me just do a last one, maybe two, just to show you. And these are a wee bit more tricky, but it's worth showing you. Right. Example 4. So I want us to integrate, and we're going to have 0 and 1 and 3y and 3 of e to the power of x squared dx dy. Right, now this is actually a really important example. So even if I just didn't say change the order of integration and evaluate, as that stands, it's impossible to integrate e to the power of x squared with respect to x. It's an impossible thing to do. Yeah, you could use one of those approximations from engineering 2, a Maclaurin series or a Taylor series around the right point and give an approximation, but it's not going to be accurate. Whereas if we change the order of integration, we can get a completely accurate answer. Right, so first thing, so we're going to put in our limits. That's x equals 3y, that's x equals 3. That's y equals 0, and that's y equals 1. Let's see what our region looks like. Right. So y as 0 and 1, and x as 3y and 3. I have to zoom out a little bit here. Right. So this is my region of integration that I'm going to have here, right? So let's copy and paste it over again. Right. Do it. Right, so these are my lines that I've got in my, so y equals 1 is this line here, right? Y equals 0 is my black line there. My red line is y equals, my green line is x equals 3. And my sloping line, which is the important one, is x equals 3y. Right, so to work out what my region is, dx is first, I'm going along the way. So the first line I hit is this line here. So that is my lower integral, and that's my second bound. So that means that this area in here is my region of integration, because the limits tell me it doesn't start to this line, x equals 3y. Right, so now I've worked out what the region is from looking at my original limits. So to change the order of integration, I need to go from dx dy to dy dx. Right, and what I also need to do is change the curve or the line that's got algebra on it, which is this one here, and if there's more than one line, you've got to change up both of them. Right, so I've got x equals 3y, and I need to change that, so that's y equals, so I just move the 3 over, so y equals x over 3. That's all I've been doing every time. So that means that blue line is y equals x over 3, or y equals a third x, whatever way you want to look at it. Okay, so that's what I've been doing every time when we've been looking at that. Right, so dy dx, that means that we work out our limits by going up the way. Right, so go up the way. The first line that starts off my region is y equals 0. That's the bottom line. Then the blue line is the bound for my region, the important line, and that's, y equals 0 and y equals x over 3. So those are the bounds of my internal integral, right? And then my dx ones, which is, where does the region start? Well, it starts at 0. And where does it end? Well, it ends at 3. So that's x equals 0 and x equals 3. Right, and I'll just substitute in, and my function in the inside stays the same. Right. Okay, so let's integrate. So I'm integrating with respect to y, so that just all stays a constant. So that's just y e the power of x squared from y equals 0 to y equals x over 3 dx. I have a feeling this is going to end up a wee bit horrible over here, but let's have a wee look. Right, so that is the integral from x equals 0 to x equals 3. Right, let's substitute in y, so that's going to be x over 3 e to the power of x squared. Take away, substitute as that 0 e to the power of x squared dx. Right, So that gives me x e to the power of x squared over 3, take away 0 dx. Right. So, got a wee issue. I've got an x multiplied by an x, sorry, I've got a function x multiplied by another function x, and I need to integrate it. Now, you can see there's a degree of 1 difference between the powers. Like that power is power of 2, that is power of 1. So that means I can use integration by substitution, right? So to do that, you let u be whatever the one is with the higher power. So we're going to let u be x squared. And then we differentiate it. So du equals du by dx equals 2 dx. So dx is du over 2x. Just write that. Right, because we know we've got to, we're going to swap the e to the power of it, sorry, the x squared for u, and that means we need to swap dx for something as well, because we want to end up with u being the only letter in our integral, if possible, because that would mean it would be an easy integration by substitution. I could have taken that third out earlier. People might be wondering why I haven't done that. I'm beginning to wonder myself. But anyway, let's substitute this in. Now, one thing I've got to remember to do is, because I've got integration by substitution, I've got to change my limits. It's my top limit. So u is x squared, so that's 3 squared, which is 9. My bottom limit is 0. So I just put this into this formula. So u equals 0 squared, which is just 0. So my integration is my integral from u equals 0 to u equals 9 x e to the power of u, because I've swapped the x squared for u, over 3 multiplied by, and dx is du over 2x. You don't need that multiply sign in there, maybe I'm just... Right. So this is something you should remember from Engineering 3. So I'll just change this to 9 and 0. We don't need to know which u now, because there's only going to be one variable in it, right? So that's x e to the power of u over 6x du, because 3 times 2x is 6x. And by doing that, you can see you've got an x on the top and an x on the bottom, so they cancel each other out. So now I've got the integral from 0 to 9 of e to the power of u over 6 du. Dead easy. You could take the 9th out if you wanted, but if you integrate e to the power of u, you get e to the power of u. So just get e to the power of u over 9, between 9 and 0. Sorry, why has that become 9? It should be 6. Beginning to believe my own hype. That wouldn't make a mistake today, but hey, it happens. Over 6. So let's substitute that in. So that's e to the power of 9 over 6. Take away e to the power of 0 over 6. And don't think that's 0. It's not. So that's e to the power of 9 over 6. take away 1 over 6. And if you want, you can type that into the calculator. E to the power of 9 divided by 6, take away 1 over 6, gives me 1350.35 units. So that's the volume that I've created in that shape. Now, one you could try that's also like integration by involving integration by substitution. I'll give you the answer. You can try it. So what you can actually do is try writing the questions from the booklet. Hopefully I've got the booklet up here. If I've not, that's not useful. Let me get it. So on your double integration booklet, which is up on Teams, as you know, if you look at worksheet 3, which is on page number 18, our question A, B, and C aren't very useful because all you're doing is changing the limits. You're not actually calculating. You can do them if you want. Right, so that's just the first bit. You're just changing the limits. You're not doing anything else. Then I would say that, yeah, D to G are all good questions. D, E, F, and G are all good questions as well. Some of them are really difficult. Right, now, there's an extra question if you want. I'll give you the answer as well. If you want to try the integral between 0 and 3 of x squared and 9, x cubed e to the power of y cubed dy dx. Again, that's one of those ones that would be impossible if you tried to do it the way it looks just now. Like, you would need to change the order of integration. And just so that you've got an answer, calculator doesn't like it. It's too big for the calculator, but the answer you should get when you work it all through is 1 over 12 e to the power of 729 take away 1. Your calculator won't be able to calculate e to the power of 729, it's too big a number. So you're just going to have to give it an exponential form like that. Right, so please try those questions. As I said, I've got a wee tiny last bit to do in polar coordinates, but I've spent so much time on a lecture on this because I needed to give more examples. These examples are a lot better than the ones I've given in previous years, and obviously because we're doing this at a distance, I want to give you more examples so it's easier for you to do.